Okay, topic 6 is going to be on exponential and log functions. The overview here for lesson 6-1. So what are some of the key features of exponential functions? For example, the domain, that's the x. And when you're looking here at an exponential function, what you should notice again is that your exponent is the variable up here. So if I have a variable up here, I can put negative numbers up there. Remember, that's like a fraction, 1 over 2 if I put a negative 1 up here. I can put positives. They can be decimals. So really my domain is any numbers. My range, the answers I can get, if I have a positive base, I cannot get a negative number for a solution because any positive number raised to any power, even if it's a negative exponent, that's like 1 over, it might get a little decimal, but no matter what, my range, my answers, I can't even get 0 here. Like if I put in a negative ginormous number, it's going to be 1 over a huge number, but that's still not 0. So there's no way to get to 0, but then it can go forever to a big number if you put a positive exponent up there. My y-intercept, remember that's when x equals 0. So if x is 0 here, when you put a 0 up here, 2 to any 0, any number to 0 is 1. We've talked about that before. My x-intercept, that means when y equals 0, remember we just said there is no way to make this thing equal 0. So unless you do a transformation on this graph to shift it down or something, there is no way to get an x-intercept on that graph. If you remember, when you look at the graph of an exponential, it kind of comes across here and shoots up sort of like that. Your x-axis is an asymptote there. Unless, like I said, if you do a minus number out here, so you're going to shift that blue graph, you're going to move this down, but that's not what we're talking about here. We're just talking about 2 to the power of x right now. So my asymptote for this, as we just said out here, is the x-axis. Remember, for the x-axis, that's the equation. Again, we've talked about that before as well. Equation y equals 0. And then the end behavior, as you go out here to the left, on the left, so as x goes to a negative infinity, that'd be like to the left, the y is approaching 0, the x-axis. And as x goes out to the right to a positive infinity, the y is going up forever to a positive infinity. So you could fill some more numbers in here if you want, but that would be your basic characteristics of a 2 to the x basic exponential function. Well, moving on then. So what if you put a number out in front that's like a stretch factor, and instead of a 2, you have a half in here? Well, what's going to happen here? On this one, I think it might actually be worthwhile to put a couple of numbers in here because it's not your normal looking function to work it out. So remember, this is like a y over here, the g of x function notation. And so I would say just try some numbers here and let's see what happens. So let's try like a -2, a -1, a 0, a 1, a 2, and maybe that'll be enough to get a general idea of what is happening. So I'm just going to grab a calculator and I'm going to type in 5 in parentheses. Instead of a half, I'm going to put a 0.5 in there just because it seems easier to type in the calculator, to the power of, and the first power I'm putting in is a -2. And I get 20 there. And the next one, I'm going to change that exponent to a -1, where that x was, and I've got a 10. anything to the 0 power would be 1 times that 5. And then I didn't see anything just print. And then if I put a 1 in there, a half times 5, that's 2.5. If I put a 2 in there, change that exponent to a positive 2. And I'm getting a 1.25. So if you look at this one, you've got your negative 2 over here. It's way up here, kind of high at negative 1. It cuts that in half. And then it crosses here at 5. That's going to cut the 10 in half. Might be a little low there. Everything's just getting half as high as you go, right? And still, so what's that called when the numbers are shrinking instead of growing? I think you've heard of this before. That's my exponential decay. So you might think about it in terms of like radiation when they do the half-life. So you have that sort of thought. So back here on my domain then, what's happening on this graph? Well, it still goes forever to the left. You can put anything you want in there. Remember, domain is like your x. So it goes forever to the left. It's still going forever to the right, but it's just getting closer and closer to 0. Your range, how low does this one go? The lowest is the x-axis. You know, that's y. Remember, range is y. So that's like 0 is the smallest it will get. And then how big, how high does the graph? It goes up for infinity. My asymptote, so we've got that x-axis again. So what's the equation for that? Remember, that's y equals 0 on the x-axis. And my y-intercept is when x is 0. And so when x is 0, that y came out to a 5. And my end behavior, as x goes to a negative infinity, that would be like going to the left, my y does what? Over here to the left, my y goes up forever. So my y goes to a positive infinity, which is like up. And on the right side, as x goes to a positive infinity, what's happening out there? When you go forever to the right here, my y is going to 0. And those would be your end behaviors. All right, let's go on to the next one. Well, so now we're saying g equals a negative 3 to the x. Now, one thing that I would say here is that what I believe they're suggesting is it's still a 3 to the x is here, and the negative goes on last, because the other thing we could also be thinking about here is what if it was a negative 3 to the x? I don't believe that is what they're asking you to. We can take a quick look at that, but that one's kind of a strange one, because if you think about this exponent, when it's odd, this is going to be a negative number, but if this is even, your answer is going to, so it's going to be kind of doing bouncing back and forth and getting bigger as it goes. So I don't believe this is what they're referring to. I think they want you to think of it as in this way. So our 3 to the x, your 3 to the x, it's just like our 2 to the x was. It's going to be going like that. Our negative outside the 3 to the x, all that's going to do, and we can, well, I'll pull up Desmos for you. So if I put my g of x over here, so this one, let's label these. This one was your y equals 3 to the x, and now I'm doing my g of x down here, but it's going to just flip it because all of your answers are going to be the same. These numbers are the same, but they're negative, so they're going to be on the bottom side. So it's like a transformation where we've flipped everything to the other side of the x-axis. So instead of my y's being positive up on the top, my y's for the transformed one with the negative in front are all going down. All right, well, how does this one work for my transformation then? We've done transformations, a lot of those. So remember, my y equals 3 to the x again is right here. There's my y equals 3 to the x. That could be considered your parent graph there. And then what's this transformation do when you put a -4 outside of the whole thing? Remember, that just lowers all of it by 4. So this was at 1 when you put a 0 in there. Y was 1. So then if I go down 1, 2, 3, 4, this new point is going to be right here. Our asymptote was 1 below that. So if we go 1 below here, that'd be at -5. I've got my horizontal asymptote now down there at -5. So it's going out here. It's going to cross there. But otherwise, it should be looking just like this graph up here. Sort of. It looks similar, but maybe not exactly the same. But that's just a transformation where the graph was moved down 4. Well, a word problem. You know, we've always got to end these lessons with a word problem. The population growth in a city since 2010 is given by the equation P of n equals 4.6. Here's my growth rate in here, because every year 1 times, if you're multiplying by this part, that's how much it is more than 1. Multiplying by 1 would mean the population stayed the same because it would never change. So here's my initial value, my growth rate, and then n is the number of years usually. And since they're saying 2040 and 2010, that's what the n would equal here. So starting value or starting population. If you take this and you subtract the 1, the 0.013, which remember that's 0.01 is 1%. So this would be the equivalent of 1.3% growth. And I believe, I don't know if it says exactly, but since we're talking about 2010 and then 2040, I think it's implied that it's the per year or annual growth rate. And then the exponent n is just the number of years it is after 2010. So this n, the number of years after whatever they tell you in the problem, which in this one it said 2010. So now they come down here and they say, well, what's the population then according to this model? So this is, you know, just, it's not, it can't be, you don't know, it's predicting into the future, you're basing it on the past. So using this model, we still have our 4.6 times 1 added on to our growth rate of 1.3%, 0.013, and then our exponent. So how many years is 2040 after 2010? And that'd be 30 years, right? So then you grab your handy dandy calculator or jump on Desmos or whatever you're using, whether it's, you know, some sort of an electronic device, your phone, and type in that formula, 4.6, and in parentheses your 1.013 to the power of 30. And miraculously, mine shows that that comes out to like 6.7770578444. Just out of curiosity here, and double check my work that I typed it in what I meant. It looks like it. And you know, I'm assuming that's the 4.6 there is probably in millions or something like that, or thousands, depending on whatever this was here. A lot of times this is either in thousands or millions, whatever the units are in this story. I don't think I wrote it down here, whatever was probably in the original problem, but this new number here, 6.77, would be in those units. I think that might be almost it. What about an exponential decay problem? So one thing that's kind of interesting on these, I think, is the 0.8. So you're multiplying by 0.8 every time. That's like 80%. But that's not the amount you're losing. And in decay problems, usually the decay refers to how much you're losing. In this formula, this refers to how much you're keeping. So I'm keeping 80% of whatever the item is. That means I'm losing 20% of the item. And so the decay in this problem would be a 20% decay. This 24 is how much I'm starting with. So I'm starting with 24 of whatever they are. Okay, in this case it says the value and it says it's in thousands. So this is a car that started out at 24,000 and decayed, depreciating, and when it's losing its value, it's depreciating by 20% per year usually would be the units on that. Okay, so the decay rate here is your 20%. It's actually 100% minus the 80%, or 1 minus 0.8 equals the 0.2, and 0.2 in decimal is 20%. Okay, so what does your y-intercept represent? So like in this problem, this 24,000 is right there. And then what does that represent? Because remember, it's decay. So every year it's going to lose value and do something like that. So the 24, which again, remember in this one was 24,000, that's your starting value of your car. Okay, so $24,000 was the starting value of the car. And we already talked about the parameters, losing or keeping 80%, so losing 20%. The practical domain. So what did the value of the car start out as? That's your 24, or if you want to do the 24,000, depending on which height, where you're at and working with it, it might want it in either form. And then it can never be a negative. Well, I don't know. I've had cars that cost me more repairing them than what they were worth. So you might say it's a negative. But the practical domain in general, I think they're after is eventually, is this thing just down to where it's worth nothing? Okay, and when will the car value be 5,000? Well, that's an equation. So we've got 5,000 equal to the 24,000. Whoops, I don't want the 5,000 though, right? Because if I'm going to use the 24 in the formula, I probably better make sure that 5 would just be a 5. So they're wanting us to solve that problem right there. Well, what do you do first? You have to get rid of the coefficient out in front. So now I've got whatever 524 says. I'll even just leave that like that. Once you have the equation down to where you have a base to a power, what is it that we have that solves when our exponent's in the power? That's our logarithm. So we have a log base 8, or base 0.8, sorry, of the 524ths. And that's what's going to equal your exponent. So those are your logs. And if you're using a calculator, if you're using a change of base property with these, you can do this like log base 10 of the 524ths over log base 10 of the 0.8, and then you can do it on any calculator. If you have a different calculator that lets you put in bases, or if you're using Desmos to put in a base, you can look up the format that you have to type that in. I'm just using a graphing calculator, and to put in a different base, you can use the math button. You go to the numbers. There's a faster way than that too. Alpha F2, there's a log base, and then you can type in the exact base. And when I just did that on my calculator, I've got 7.0296. Okay, so maybe I'll just jump over and let's look up how you would do that in Desmos as well, in case somebody get a new screen here. And I'll share that with you so you can follow along with me. So I'm just going to type in here Desmos log format. And so it says when you're going to type it in, you do y equals log. Let's see, log. So you just put the base right down in there, it looks like. All right, well, let's double check. Let's just try that. So I think I had log base 8 of 5. So log base 0.8. So that's not going to put it down there. So I just put a space or an underline right there. So the format, and then arrow to the right to get the 5. So there's my negative 7.21256. Hopefully. So I'll write it on the screen here. 7.0296. Oh, it was log base 0.8 of 5/24. So 5/24. So I don't think that's what I did. 5/24. Oh boy, that's not what I wanted. So there may be some parentheses in here. 5/24. 7.02962. That sounds familiar. Again, let's switch that back then here. 7.0296. Okay, so those matched up. Just to again, what I typed in Desmos then was y equals log. I did a underline, like shift and the dash, and then the 0.8, and then Desmos knew to put the 0.8 as the base, and then in parentheses 5/24 for it to give me this same. And how about now we have a sculpture that's worth 50 and the value that they gave us, which had a higher growth rate from year 0 to 5, they're asking. This one or this one, the growth rate. So my growth rate over here, remember we said we take the 1.075 and subtract off the 1. So we have a 0.075 or 7.5% growth rate from year to year. And then we're going to come over to the numbers they gave us on this one. Well, how do we figure out what that amount is that it's growing by over here? So I have, I'm looking at these numbers and saying, is it 1,000? That point is 1,000, 40. That doesn't really make sense. I don't know what this, if this is 5 and 604 or 64.4, this 40 can't go to 64.4. That would be going down, not up. I think I better look something up on that lesson to see if I can figure out. I must have copied something wrong in the problem when I looked at that. So it's 0, excuse me, 0, 40. It's in thousands. Okay, so these are, so this point is the 40. These numbers are in thousands of dollars. So this represents 40,000, that's 64.4 thousand. So how much did that go up? So that went up from 40 up to 64.4. So it increased by a value of like 24.4. But for how many years was that? Because it's like we have this equation, but we don't know our growth rate. So we know that we have the 0.040, and we know we have the 0.5, 64.4. We know it's exponential, so it's the equation like y equals starting value times your multiplier to your growth rate. We do know our starting value right there. We do know that that's 40. We do not know this base amount or the rate that it's growing. Sorry, the starting value times, this formula is a little wonky here. It's the rate to the number of years. I don't think I wrote that right. Let me back that up. My growth rate is supposed to go here, and then the number of years is up there. All right. So then what we've got here is we've got our 64.4 that we know it's worth. We know it started out at an amount of 40. We don't know that growth rate. That's what we want to figure out. We know this was 5 years later to go from 0 to 5. So then you should be able to solve that equation. Again, what do you move first? Divide by this 40. 64.4 divided by 40 on my handy dandy calculator here. 1.61 equals my r to the 5th now. And how do I get rid of the 5th power? I will use my properties of exponents. You could do a 5th root, but I'm going to remind you that if you do powers to powers, we want an r to the 1st. 5 times 1/5 would be 1. So if I raise both sides here to the 1/5 power, that's going to give me my r. So I grab my calculator and I just put in the 1.61 to the power of, in my exponent, 1 divided by 5, and get a 1.0999. So remember, my growth rate again here is take the 1 off. So it's, move the decimal over 2 would be 9.99%. And we're comparing that to over here, the 7.5%. And so the growth rate here on this painting is greater. So that's how you could take 2 points. If they gave you 2 points, you know it's exponential growth rate, how much is growing by year from 1 year to the next. And then if you follow that same procedure, starting amount, they gave us that, times our rate, we don't know that. We knew it went from 0 to this was 5, so it was over 5 years. That's why the 5. Divide by this starting value to get the rate alone. Base to a power, after you have your base to a power, that's when you rewrite it as a, your power is, you want to get it at 1 up there, so 5 to the 1/5, the reciprocal. Both sides, and there we have it. That's a pretty long lesson there. Thanks for watching.